Hey, let's talk about polar and nonpolar molecules. In order to understand polarity, we need to begin with a covalent bond. And we said before that a covalent bond occurs when two atoms share a pair of electrons. But it turns out those atoms don't always share those electrons fairly between the two. Some elements are more electronegative than others, and what that means is they pull on those bonding electrons more than the other element pulls back. So those bonding electrons spend more time next to the more electronegative element. Fluorine happens to be the most electronegative element on the periodic table. And the electronegativities have been measured for all the elements, and there's a table that lists those values, but we don't need to look up the table. Instead, just know the trend. The trend is the closer the elements are located next to fluorine on the periodic table, the more electronegative they will be. So you might expect oxygen, sulfur, and chlorine to be fairly electronegative, and that's true. They're close to the fluorine. And then carbon, silicon, those elements are getting farther from fluorine. They're less electronegative. Okay, what does that mean? Well, let's look at an example. Let's look at the molecule HF. Just hydrogen and fluorine bonding together. Fluorine's the most electronegative element. Poor hydrogen's really far away from fluorine, so it's not very electronegative at all. When we draw the Lewis dot structure, we'll just review that real quickly. Fluorine is in column 7A, so 7 valence electrons. Hydrogen is the first element, has 1 electron. Just push the atoms together so their single electrons can pair up, and you make a molecule of hydrofluoric acid, HF. Okay, and the line represents 2 shared electrons, but fluorine isn't sharing very fairly. It's like the hydrogen and the fluorine are in a tug-of-war, and fluorine is winning. So this pair of electrons is spending more time close to the fluorine, and that's making fluorine feel negative. If fluorine had both electrons, it would be a -1 anion. Well, hydrogen's not letting go. So fluorine is starting to feel negative because it's winning the tug-of-war, but it's not fully negative, it's just slightly negative. And we use a little delta, the Greek letter delta, to represent partial or slight. So there's a slight negative charge on fluorine. Hydrogen is losing the tug-of-war, so it's starting to feel positive. Those electrons are leaving, but not completely. Hydrogen's not letting go, but hydrogen is starting to feel a little bit positive. It's almost a cation. So the delta means partial, a slight charge. And now we can talk about the bond being polarized. The hydrogen-fluorine covalent bond is polarized in the sense that fluorine is seeing more of those electrons than hydrogen, so there's a buildup of negative charge on the fluorine. And that makes for a polar covalent bond. Not all bonds are polar, but most are. Most covalent bonds are polar. When the bonding electrons are shared fairly, then it's nonpolar. That makes a nonpolar covalent bond, and that's going to happen when you have the same two atoms from the same element, or carbon and hydrogen appear to have very similar electronegativities. They pull on the bonding electrons with about the same force. And so a bond between carbon and hydrogen is also nonpolar covalent. Okay, what consequences does that have? Well, if the molecule contains polar covalent bonds, and they don't cancel out, that makes the molecules polar themselves. And if they do cancel out, if the polar covalent bonds do cancel out, or if there are only nonpolar covalent bonds, then you have nonpolar molecules. Okay, let's explore that a little bit more with some examples. Let's look at the following molecules and decide if they're polar or nonpolar. Okay, first of all, you have to make sure you have the correct Lewis dot structure. So here's a Lewis dot structure of hydrofluoric acid. Then you need the periodic table. And you have to know that fluorine is the most electronegative. So hydrogen is losing the tug-of-war here. It's slightly positive. Fluorine is slightly negative. And if you can find one end of the molecule, looks like the left side is slightly positive, and another end of the molecule, right side, slightly negative, that makes the molecule polar. And it's polar because it has a polar covalent bond. Let's look at the next molecule. Now carbon is making 4 single bonds here. Hydrogen each makes 1 bond. Fluorine makes 1 bond. And get the right Lewis dot structure here. Fluorine and carbon each have an octet of electrons. Good Lewis dot structure. Hydrogen has a pair of electrons each. Okay, now let's classify each of the bonds. Well, the carbon-fluorine bond here is a polar covalent bond, right? Fluorine's the most electronegative. Carbon is losing the tug of war, so put a little delta plus. It's the carbon atom slightly positive, fluorine slightly negative. And that bond between carbon and fluorine is a polar covalent bond. There's a top bond here between carbon and hydrogen. We're just going to have to remember that that's a nonpolar covalent bond. There's another CH bond on the left, another CH bond on the bottom. The nonpolar covalent bonds you just ignore. So this molecule contains a polar covalent bond. The right side of the molecule is slightly negative, the left side slightly positive. That's a polar molecule. How about carbon dioxide? We saw this Lewis dot structure before. Okay, carbon is making a double bond to each oxygen. Let's just look at the top covalent bond. What kind of bond is that? Is that a nonpolar covalent bond or a polar covalent bond? Let's go to the periodic table. Oxygen is right next door to fluorine. Carbon's farther away. And so oxygen being close to fluorine, it's more of a bully. It's also very electronegative. Carbon's farther away, less electronegative. So this top bond is a polar covalent bond. Oxygen is more electronegative than carbon. Carbon's slightly positive. Same is true for the bottom bond. The bond on the left side, same thing. Oxygen is more electronegative than carbon. And I'll just leave the same delta plus sign here for carbon, not add another one. So this actually has four polar covalent bonds, but the left side of the molecule is slightly negative, and so is the right side. These covalent bonds, these polar covalent bonds, are canceling out. It's like a tug-of-war. The carbon and the oxygens are in tug-of-wars here, and this oxygen on the right is yanking the bonding electrons to the right, whereas the oxygen on the left is yanking the covalent bonds, the bonding electrons to the left, and there's no net swing of electrons. Sure, carbon is feeling positive, but this end of the molecule is negative, and so is this end. The bond polarities, the arrows, are equal in opposite directions. They're canceling out. Carbon dioxide then becomes a non-polar molecule, but it has four polar covalent bonds. It's a nonpolar molecule because those covalent bonds are canceling out. Let's look at water. Oxygen, it's right next to the fluorine. Hydrogen's on the other side of the periodic table. It's losing the tug-of-war. Hydrogen's feeling positive. Oxygen is negative. Same is true for both bonds. Now, when we look at this molecule, we would say, hey, this bond right here is polarized inward towards oxygen. This bond on the right also polarized inwards towards oxygen. Oxygen's more electronegative. Don't those bonds cancel out? It looks like it's a nonpolar molecule. Well, I'll put a question mark here. Turns out you may have heard that water is very polar. So what's going on? It turns out this Lewis dot structure is a correct one, but it has the wrong shape. The correct shape is a bent shape. When I drew the water molecule, I put the hydrogens in either side, but I could have chosen to put them in this arrangement or in this arrangement. It turns out these last two or last three structures are closer to the actual shape of water. And now the bond polarities are pointing in towards the oxygen. They both point up. This one's pointing to the right and up. This one's pointing to the left and up. The left-right components are canceling, but they're both up. Another way to look at this is that the bottom, if you consider this resting on a surface, the bottom of the molecule, two hydrogens, both positive here. This is a positive end of the molecule. The top is negative. It turns out water is a polar molecule. That's the correct answer. So it turns out the shape of the molecule is important for determining polar molecules. So now we need to know how to predict the shape of molecules. Well, the shape of a molecule is determined by those electrons that are shared between the atoms and those lone pairs. The electrons simply repel other electrons, and they force the atoms to shift around so that the electrons can get as far away from each other as possible. Let's look at some common shapes of molecules. Okay, Here's some drawings. If we have a central atom, it's letter A here, and there's a pair of electrons to its left, a pair of electrons to its right. Oh, this is actually showing the orbitals, the locations where the electrons hang out. So if you put 2 electrons here and 2 electrons here, this pair of electrons is going to repel this pair. And they're going to get as far apart as possible, which means they're going to be on opposite sides of the atom. Here's an example. Beryllium makes 2 covalent bonds. And if we attach chlorine to them, the chlorine atoms are going to be on each side of the molecule. That makes for a straight or linear shape of the molecule. Boron here makes 3 bonds. This pair of electrons, this pair of electrons, this pair of electrons. Those 3 pairs are going to shift and move and get as far apart as possible to form a triangle shape, a flat triangle, or trigonal planar. Now in this example here we got carbon attached to 4 hydrogens. Carbon likes making 4 bonds. So these 4 bonds have electrons in them that are repelling, and it turns out the way this molecule is drawn, it looks like a flat square. Well, that's thinking 2-dimensionally. The molecule can spread out in 3 dimensions and get into this shape, which is a tetrahedron. And if you want to try and draw it correctly on paper, you can use these dash bonds to show the bonds that are going back into the page. And you can use a wedge bond to show the bonds that are coming out of the page. It's sort of like a perspective drawing that gets bigger as it approaches you. At any rate, when we see a molecule drawn with 4 bonds or 4 pairs of electrons around it, we'll just have to think 3-dimensionally and know that the molecule spreads out like a tetrahedron. Now let's explore the tetrahedral shape a little bit more. Carbon makes 4 bonds, and so these bonding electrons spread out into the tetrahedral shape. In the middle we have ammonia, NH3, and it turns out when you draw a Lewis dot structure, nitrogen is going to have a lone pair of electrons that are not being bonded to anything. Nitrogen needs 8 dots around it, so there's the pair up here, a pair here, a pair here, a pair there. There's 8 dots around nitrogen. It just happens the top pair is not attached to another atom. They're not being shared. Well, they're still there. That's what this cloud is showing. The electrons are hanging out above the central atom, and these electrons are going to repel the other pairs of electrons and force the molecule into this shape. So it's kind of like a pyramid with a triangle base, so trigonal pyramid. And finally, water has 2 lone pairs. And these non-bonding pairs, these are going to repel the bonding pairs. There's 4 pairs of electrons, just like there's 4 pairs of electrons in CH4. This is also known as methane. If you just look at the electrons around oxygen, they too have a tetrahedral shape, but when we think about shapes of molecules, we don't think about the electrons, we think about the nuclei, or the atoms themselves. So there's no atoms up here, so we ignore those regions, and we just think about water being bent. But it's forced into a V shape or a bent shape because of the lone pairs, as well as the bonding pairs. So how come we have to identify molecules as either polar molecules or as nonpolar molecules? Well, maybe you've heard of the expression oil and water do not mix. Well, oil and water don't mix because oil happens to be a nonpolar molecule. Turns out oils are made up of molecules containing only hydrogen and carbon, so those types of molecules are called hydrocarbons. And hydrogens bond to carbon, and carbon bonds to carbon through nonpolar covalent bonds, right? The CH bond, we just have to remember that's a nonpolar covalent bond. And 2 atoms of the same element, CC, those are also going to be nonpolar covalent. They're going to share fairly. Okay, oils are nonpolar molecules. Water, we just saw, is a polar molecule. It has a bent shape. Slightly positive down here, slightly negative there. It's a polar molecule. Well, polar molecules tend to stick to polar molecules. Nonpolar molecules are kind of forced out, and they don't mix. That leads to another little guideline called like dissolves like. That just means if a molecule is like another molecule, they should dissolve or mix together. So polar molecules dissolve in other polar molecules. So salt, well, the Na is a positive cation, chlorine is a negative anion. Yeah, one side's positive, one side's negative. That definitely is a very polar molecule. So salt is polar, water is polar. Salt dissolves in water. Nonpolar molecules dissolve in each other. The old mechanics used to wash their hands in gasoline because oils and grease are nonpolar molecules. Gasoline turns out to be a nonpolar molecule, and they're all nonpolar molecules. They dissolve each other. So gasoline does dissolve oils and grease off your hands. So here we go. We can apply that and make some predictions. There's an oxygen-hydrogen bond at the end. That's a polar covalent bond. There's also a bond between the carbon and the oxygen. That's also a polar covalent bond. Turns out they're not going to cancel out. The oxygen's going to be bent again. This molecule is going to be polar. Water is polar, so they should dissolve each other. And we say that their molecules are soluble. What about CCl4? Well, 4 chlorines, each bonding the carbon. Those are actually polar covalent bonds. Chlorine is more electronegative than carbon, but there's 4 of them. 4 bonds to carbon makes a tetrahedral. Those bonds are all going to cancel out. They're all pointing in opposite directions. They're all canceling. So CCl4 is a non-polar molecule. What about the top molecule, 4 carbons and a bunch of hydrogens? Well, all those bonds are going to be non-polar covalent bonds. They're all bonds between C and H, and they're all bonds between C's and C's. So hey, this molecule is also nonpolar. They're both nonpolar molecules. They should dissolve each other. And then over here we have 3 carbons and a bunch of hydrogens. That's nonpolar. And then we have water. Oops. We have a polar molecule trying to mix with a nonpolar one. Nope. They're not going to mix in each other. We say that they are insoluble. Okay, that's enough for now. I'll see you in class.